The Morning Glory Spillway, also called the Glory Hole by locals, is the largest drain in the world. A spillway is a structure used to provide the controlled release of water from a dam or levee downstream, typically into the riverbed of the dammed river itself. In the United Kingdom, they may be known as overflow channels. Spillways ensure that water does not damage parts of the structure not designed to convey water. Spillways can include floodgates and fuse plugs to regulate water flow and reservoir level. Such features enable a spillway to regulate downstream flow. By releasing water in a controlled manner before the reservoir is full, operators can prevent an unacceptably large release later. Other uses of the term spillway include a bypass of dams, and outlets of channels used during high water, and outlet channels carved through natural dams such as moraines. Water normally flows over a spillway only during flood periods, when the reservoir has reached its capacity and water continues entering faster than it can be released. In contrast, an intake tower is a structure used to control water release on a routine basis for purposes such as water supply and hydroelectricity generation. A spillway is located at the top of the reservoir pool. Dams may also have bottom outlets with valves, or gates which may be operated to release flood flow, and a few dams lack overflow spillways, and rely entirely on bottom outlets. The two main types of spillways are controlled and uncontrolled. A controlled spillway has mechanical structures or gates to regulate the rate of flow. This design allows nearly the full height of the dam to be used for water storage year-round, and floodwaters can be released as required by opening one or more gates. An uncontrolled spillway, in contrast, does not have gates. When the water rises above the lip or crest of the spillway, it begins to be released from the reservoir. The rate of discharge is controlled only by the height of water above the reservoir spillway. The fraction of storage volume in the reservoir above the spillway crest can only be used for the temporary storage of floodwater. It cannot be used as water supply storage, because it sits higher than the dam can retain it. In an intermediate type, the normal level regulation of the reservoir is controlled by the mechanical gates. In this case, the dam is not designed to function with water flowing over the top of it, either due to the materials used for its construction or conditions directly downstream. If inflow to the reservoir exceeds the gate's capacity, an artificial channel called an auxiliary or emergency spillway will convey water. Often, that is intentionally blocked by a fuse plug. If present, the fuse plug is designed to wash out in case of a large flood, greater than the discharge capacity of the spillway gates. Although many months may be needed for construction crews to restore the fuse plug and channel after such an operation, the total damage and cost to repair are less than if the main water retaining structures had been overtopped. The fuse plug concept is used where building a spillway with the required capacity would be costly. Chute spillway. A chute spillway is a common and basic design that transfers excess water from behind the dam down a smooth decline into the river below. These are usually designed following an OG curve. Most often, they are linked on the bottom and sides with concrete to protect the dam and topography. They may have a controlling device and some are thinner and multiply-lined if space and funding are tight. In addition, they are not always intended to dissipate energy like step spillways. Chute spillways can be ingrained with a baffle of concrete blocks, but usually have a flip lip and or dissipator basin, which creates a hydraulic jump, protecting the toe of the dam from erosion. Step channels and spillways have been used for over 3,000 years. Despite being superseded by more modern engineering techniques such as hydraulic jumps in the mid-20th century, since around 1985 interest in step spillways and chutes has been renewed, partly due to the use of new construction materials, like roller compacted concrete, gabions, and design techniques embankment overtopping protection. The steps produce considerable energy dissipation along the chute and reduce the size of the required downstream energy dissipation basin. A bell-mouth spillway is designed like an inverted bell, where water can enter around the entire perimeter. These uncontrolled spillways are also called Morning Glory, after the flower, or glory hole spillways. In areas where the surface of the reservoir may freeze, this type of spillway is normally fitted with ice-breaking arrangements to prevent the spillway from becoming ice-bound. In some cases, bell-mouth spillways are gate-controlled. The spillway at Hungry Horse Dam, in Montana, the U.S., the highest Morning Glory structure in the world, is controlled by a 64 by 12-foot ring gate. One of the most well-known of these spillways is the one in Cavao dos Conchos Reservoir Lake, in Portugal, which is constructed to look like a natural formation. A video of this went viral on the internet in early 2016. The largest bell-mouth spillway is in Geehee Dam, in New South Wales, Australia, measuring 105 feet in diameter at the lake surface. A siphon makes use of the difference in the height between the intake and the outlet to create a pressure difference needed to remove excess water. Siphons, however, require priming or the removal of air in the bend for them to function, and most siphon spillways are designed with a system that makes use of water to remove the air and automatically prime the siphon. One such design is the volute siphon, which makes use of water forced into a spiral vortex by volutes or fins on a funnel that draws air out of the system. The priming happens automatically when the water level rises above the inlets used to drive the priming process. One parameter of spillway design is the largest flood it is designed to handle. The structures must safely withstand the appropriate spillway design flood, sometimes called the inflow design flood. The magnitude of the SDF may be set by dam safety guidelines, based on the size of the structure and the potential loss of human life or property downstream. The magnitude of the flood is sometimes expressed as a return period. A 100-year recurrence interval is the flood magnitude expected to be exceeded on the average once in 100 years. This parameter may also be expressed as an exceedance frequency, with a 1% chance of being exceeded in any given year. The volume of water expected during the design flood is obtained by hydrologic calculations of the upstream watershed. The return period is set by dam safety guidelines, based on the size of the structure and the potential loss of human life or property downstream. The United States Army Corps of Engineers bases its requirements on the probable maximum flood and the probable maximum precipitation. The PMP is the largest precipitation thought to be physically possible in the upstream watershed. Dams of lower hazard may be allowed to have an inflow design flood less than the probable maximum flood. As water passes over a spillway and down the chute, potential energy converts into increasing kinetic energy. Failure to dissipate the water's energy can lead to scouring and erosion at the dam's toe base. This can cause spillway damage and undermine the dam's stability. To put this energy in perspective, the spillways at Torbella Dam could, at full capacity, produce 40,000 MW, about 10 times the capacity of its power plant. Spillway gates may operate suddenly without warning, under remote control. Trespassers within the spillway are at risk of drowning. Spillways are usually fenced and equipped with lock gates to prevent casual trespassing within the structure. Warning signs, sirens, and other measures may be in place to warn users of the downstream area of a sudden release of water. Operating protocols may require cracking a gate to release a small amount of water to warn persons downstream.